Friend, today we are discussing another topic on DC transients, but here we are doing an example. Question regards an RL or a resistor inductor series connection DC circuit. Question says, with the aid of transient curves, explain how the following parameters vary with time in an RL circuit. Part 1, induced voltage VL. Part 2, resistors voltage VR. Part 3, supply current I. Part B says an inductor has negligible resistance and an inductance of 200 millihenries and is connected in series with a 1 kilo ohm resistor across a 24 volt DC supply. Therefore, determine time constant, the steady state value of the current flowing in the circuit, the current flowing in the circuit at a time equal to 2 times the time constant, and finally, also we are required to determine the voltage drop across the inductor at a time equal to 2 times the time constant. So let us look at solutions. So A, let us look at the induced voltage in the inductor. When we draw values of inductor voltage against time, we get a curve that looks like this, an exponential curve that shows voltage decay with time. So this curve shows decay of induced voltage with time and is given by the equation VL equal to V exponent negative R out of LT, and this is equal to VE negative T out of tau, whereby tau is the time constant given by L out of R. So we see that this curve or this graph shows exponential decay of voltage. Part 2, let us look at resistor voltage. When we plot values of resistor voltage against time, we get a curve which undergoes a transient up to a value of VR equal to V when it attains steady state. This is steady state, and this part represents transient period, the period that takes place after the closure of the switch. Just after the closure of the switch, this one happens within the circuit, and later on, after a very short period of time, the voltage reaches its final steady state, where the voltage across the resistor is equal to the source voltage. It is obtained by this graph is obtained by values of VR, which is equal to V equal to 1 minus exponential negative R out of LT, and this is equal to V into 1 minus E negative T out of tau, whereby V the source voltage and tau is the time constant. So this kind of graph implies that at T equal to infinity, or as time goes by, after a long period of time the circuit has been switched on, the inductor acts as a short circuit. In other words, it will just act as a wire and the current will just be flowing through it. Now let us look at our part B. Now we are given that the inductance is equal to 200 millihenries and the resistor is 1 kilo ohm, 1 times 10 to the power 3 ohms, and the voltage, source voltage V, is equal to 24 volts. So time constant is equal to L out of R, and it is equal to 200 exponent negative 3 to convert it to henries, divided by 1 exponent 3 to convert it to ohms, and this would give us 0.2 milliseconds. Roman 2 is steady state value of current, and from I as a function of time, this formula for calculating current across an inductor resistor series connected DC circuit is equal to V out of R into 1 minus E or exponent of negative T divided by tau. Then if we substitute in, of course, at steady state value of current, we know that this happens when T is equal to infinity. In other words, after some time. So after some time, let us take it to be t, which has moved close to infinity. So from the above, if we substitute in our value for t equal to infinity, this one will go to 0, and therefore, because the exponential of a very big value, time means here the time we are going to put a very big value, and therefore divided by that, this will, the whole of this will be equaling to 0, and therefore we will remain with V out of R. So if we remain with that, the steady state value of current will equal to V out of R, and is equal to 24 divided by 1 exponent 3, which gives you 24 exponent negative 3 amperes. What about the supply current? The supply current is equivalent to V out of R into 1 minus exponent negative T out of T. So when we want the supply current at T equal to 2 times the time constant, we shall just substitute in that value of T, which is twice tau. When we substitute it in here, we shall have, and the other values for V out of R will be 24 exponent negative 3 into 1 minus E of this. This will go, so it will be exponential of negative 2. So this value 1 minus exponent of negative 2 is 0.8647. So times that, we shall get 20.75 milliamps. What about the voltage drop across the inductor at T equal to 2 times the time constant? We know that the voltage drop across the inductor is VL equal to V exponential of negative T divided by tau. When we substitute in our T, which is twice tau, then this one and that will go, and we remain with 24 exponent of negative 2, and the value that we get will be 0.13534 times 24, which is our volt. Then this will voltage source times this value, which we have already gotten here, exponential of negative 2, we will have 3.24 volt. Thank you so much.